Welcome. I'm Ozer, and I'm presenting our work, cross-domain artifact correction of cardiac MRI. To begin with, I would like to mention some brief information about medical image quality issues. We'd like to ensure high image quality during a medical test so that the clinicians can assess the image more accurately in terms of diagnosis and come up with an adequate treatment. However, not always we can have an image with high quality at the time of acquisition. This may be caused due to motion artifacts, which are the primary effect of problematic breath-holding capability, or the cardiac rhythm of the patient, or a faulty ECG signal, whose consequence is shown on the right image. While the types of image quality issues are not restricted with the motion, we can use CNNs to undermine the prevalence of motion artifacts and improve the image quality. This will also help to improve the performance of the following sequential steps, such as cardiac tissue segmentation and diagnosis. In this regard, we start with the question of what we can do in order to increase the effectiveness of the deep neural networks to overcome the problem-specific medical image quality issues, such as Gaussian noise or mistriggering artifacts in cardiac magnetic resonance imaging. Although the presence of Gaussian noise is an image domain-based quality problem, which can also be solved on the image domain, mistriggering artifacts is a frequency domain-based problem, which directly affects its image domain representation as well. More specifically, the former can intuitively be solved on image domain, although the latter is highly affiliated with the case-based domain alongside image domain, and hence the correction of CMR images should be applied on both of these domains. We are also interested in whether the network is capable of correcting the images that are the problem sources in the image domain, and the correction is performed on the frequency domain, or vice versa. Our contributions are as follows. First, we generate 4 different building blocks to measure their effectiveness over a number of image quality problems, such as image denoising and mistriggering artifact correction. We then test them on 2 different network architectures which resemble UNet and DNCNN. Then we show that the building block, which involves processing on both image and case-based representations, improves the mistriggering artifact correction task after comparing it with 3 other building blocks. We have 4 different building blocks, where the most basic one involves convolutional, batch normalization, and activation layers in a sequential order. We define it as baseline convolutional block working on image domain, which does not involve any processing on the image frequency domain. We then create its frequency domain counterpart by taking the 2D fast Fourier transform of the representation, process the real and imaginary parts separately, and finally, taking the 2D inverse fast Fourier transform of the representation. We name this block as baseline convolutional block working on the frequency domain. Then we generate the enhanced convolutional block by cascading the output of a BCBI layer with the average of a 2-branch BCBI mechanism. Finally, we construct our cross-domain model by stacking BCBI and BCBF on the top of each other, which we name it as enhanced convolutional block with image and frequency components. In all of these building blocks, we set the convolutional filter size to 64 and kernel size to 3 by 3. In our work, we utilize UNet and DNCNN architectures, where we create them by using the aforementioned building blocks. In both of these architectures, our purpose is to improve the quality of the images by either denoising or correcting the mistriggering artifact as shown above. We use 2 different datasets which are named BSDS-300 and Automated Cardiac Diagnosis Challenge. BSDS-300 is a cover image dataset which we use to understand the capability of our building blocks for photo image denoising. We use 200 of the images for the training and leave the 100 images for evaluation. In addition, ACDC is a short-axis CMRI dataset in which we perform denoising and synthetic artifact correction. We split the dataset into two subsets where we use 100 patients for training and 50 for testing. Also, we only worked on the systole and diastole phases of the dataset. We would like to mention the implementation details as well. We use the BSDS 300 dataset for denoising and the ACDC dataset for both denoising and mystery green artifact correction, which are denoted by the letters D and AR respectively. The standard deviation of the additive white Gaussian noise is set to 30, while the correction ratio of the artifact correction is 0.15. All of these models have been trained for 200 epochs with a batch size of 64, while Adam optimization function is used to optimize the mean squared error loss. We perform a quantitative analysis where we measure the performance of 4 building blocks within the DNCM and UNet models. We compare the performances of these models in terms of the peak sequence to noise metric, which is one of the primary metrics when it comes to image quality analysis. For the denoising task of BSDS dataset, we achieve comparable results as a result of using BSBI and ECB blocks, which both work on the image domain. Although frequency domain-based building blocks, BCBF and CBIFC, work up to some extent, they still fall behind the image domain-based building blocks. We also see this pattern for the denoising task of the ACDC dataset, where the use of ECB block outperforms all of the other building blocks. However, when it comes to the mystery ring artifact reduction of the ACDC dataset, using the cross-domain block significantly improves the PSNR metric over other building blocks. Furthermore, due to the instability of the training using the BCBI blocks, we even observed a fall in the PSNR comparing the uncorrected version of the mystery ring artifacts. We see that the use of baseline convolutional block working on the image domain and enhanced convolutional block effectively demonstrates a satisfactory performance for the image denoising task. Here, we note that using the cross-domain blocks for mistriggering artifact correction efficiently improves the image quality over the baseline blocks working on image and frequency domains and enhanced convolutional blocks. So here are our conclusions. First, we propose a series of building blocks for image quality improvement, which we found out that involving processing on frequency and image domain sequentially has significantly improved the results for 2 different architectures comparing other variants. We also observed that building blocks should be picked accordingly, depending on the problem of interest that it will be useful to work on the image domain for denoising and both image and frequency domains for misreading artifact correction. As a future work, we are planning to work on multiple sources of image quality issues on the images, such that denoising and artifact correction will be done simultaneously. Also, since these image quality issues are generated synthetically, we plan to extend our approach on real-world datasets with authentic MRI artifacts as a future work. Here are the references. I want to thank you, my co-author, Ilkay, Oksuz, and our founding bodies. We will be open sourcing our code to make our research reproducible. Thank you for listening.